Okay, so this is going to be a very short video, but I've just wanted to cover uh, one more topic from this section. I am going to cover the very last thing in this section, 22.6, about the space of functions as a metric space, but that's going to be in a future lecture. So this is going to be the last thing from section 22 that we talk about for now. And it's basically, so it's going to be about the idea of path connectedness, which is basically a formalization of the intuitive idea that there's a concept of connectedness that applies when a space has a property such that any 2 points in the space can be joined by a path which stays inside of that space, basically, right? This is a very intuitive idea. I mean, I even kind of alluded to it before when I was talking about connectedness itself, when we were talking about like intervals, for example, and I was saying, okay, you can't cross from one piece of this disconnected interval, you know, where there was like a deleted point in the middle, right? You can't cross from one side to the other without hitting a point that's like not inside of the set, right? So the same thing will be, I mean, that's exactly the idea that we're going to be, you know, using in path connectedness. So let's just sort of make the definition here. So given a metric space S, a path in S, is a continuous function gamma a b into S. Okay, so just any continuous function from a closed interval into the space S. We already saw examples of this with like S equals RK, right, where we were talking about like parametric curves in higher dimensional spaces and stuff. Those are examples of paths. Okay, so you can define a path for an arbitrary metric space. And then we'll say that we say E subset S is path connected if for all pairs of points in E, there exists a function, a path in E. So I'm going to circle that because that's important. Such that gamma of A equals S and gamma of B equals T, right? So one endpoint is S, the other endpoint is T, you have a path, right? Obviously, this is continuous because it's a path, okay? So a path from S to T. Okay, so it's a very simple idea, and the only thing we're really going to say about it for now is that, okay, so actually let me just go to a new page here. Strange. Right, okay, there we go. So the only thing I'm going to say about it for now is this theorem. Very quick proof here. So if E in a metric space S is connected, then E is path connected. Okay? And perhaps surprisingly, it doesn't go the other way. So there are, or sorry, I got this flipped. If E is path connected, then E is connected. So there are actually connected spaces which are not path connected. I'll mention an example at the very end, but I'm not really going to go through rigorously the proof of why. Maybe you can think about it for yourself. That could be a good exercise. But yeah, anyway, so let's see. So if E is path connected, then E is connected. So here's the proof. Suppose E is disconnected by U1 and U2. then there exists an S in U1 and a T in U2. It's a very simple idea, right? Like U1 and U2 are supposed to divide E into two disconnected pieces. So the point is we'll just show that that's impossible, because if you do that, if you try to do that, you can take a point in one piece and a point in another piece and join them by a path, and that shouldn't be possible, right? So, so there exists gamma connecting them. Then gamma of A, B is a subset of E, and it's connected by the previous theorem, right? Our theorem about images of connected sets under continuous functions, right? Says that this set has to be connected, but U1 and U2 disconnect gamma, right? They disconnect gamma because gamma is a subset of E, and U1 and U2 disconnect E, and gamma has a point in U1 and a point in U2, right? So if you just go through, I mean, it's sort of trivial, but if you go through all the pieces of the definition of disconnecting, you'll find that you can show that U1 and U2 disconnect gamma. I mean, it's barely even showing. It's like almost immediate. It's almost trivial. So, but I mean, maybe just go through verifying that yourself. But yeah, this shouldn't be possible. So this is a contradiction. E is connected. Okay, so that's that. And let me just mention this example of a connected but not path connected set. The closed topologists sine curve in R2. So R2 is a Euclidean space, obviously, right? We've seen this, it's the graph, sorry. Let me just quickly sketch this. So we have, you know, something like that. And then it gets very, you know, and then, so as a subset of R2, right, this is the graph. Sorry, it's supposed to be a bit more even here. Not that it really matters. So this is the graph, right, of f of x equals sine of 1 over x for x greater than 0. So we're saying as a subset of R2, we're using the graph, right? It's not just the function, okay? The function itself is only part of the picture here. The actual set we're talking about is the graph of the function in R2, okay? The graph is the connected set, but only, so you add, so if you add the piece of the y-axis, so add the interval -1, 1 on the y-axis. So the set of points on the y-axis between y equals -1 and y equals 1, if you add those into this set, okay, then you get a closed set. And it turns out that it's connected, but it's not path connected. And the reason it's not path connected is because if you try to make a path from any point on the actual curve itself, on the actual graph, you can't make a path from a point on the graph to a point on the interval over here, okay? It's impossible because the path, you know, the function defining the path would have to go through this like infinite number of oscillations in order to get to any point over here, and that's just like not possible. It's not possible to do that if it's a continuous function on a closed interval. So yeah, so this is actually connected but not path connected. Anyway, So that's all for this lecture. I know it was a little bit on the long side, but the good news is that the next lecture will be relatively light. So thank you for sticking it out, and I'll see you then.